children are our future. Some of them take their first faltering steps, others enjoy their first success and life through the first defeat. They dream to grow up and become fearless explorers, outstanding sportsmen or authors of major scientific inventions. It will take them quite a little time to start bringing their dream to life. What will the world be like for them? What have we done to protect the planet for our children? This is the map of Russia with the marked locations of temporary radioactive waste storage facilities. Such objects appeared on the country map as a result of the active nuclear energy use, following implementation of the USSR defense programs. Nuclear power icebreakers and submarines guarding the interests of our country. Nuclear power plants producing electricity, special medical and research equipment. Their overall operation leads to the emergence of radioactive wastes, which are being stored in the temporary burial sites. Those ones are designed for 30 to 50 years. However, temporary storage will not solve the problem of radiation safety in the future. What are radioactive wastes? What to do with them further on? And why is it necessary to think nowadays about construction of final disposal facilities for the radioactive waste to be safely isolated in order to secure the ecological well-being in the future generations? We are to find answers to these questions together with you today. The volume of radioactive wastes accumulated in our country over the past 70 years is more than 500 million cubic meters, which are already within the country's territory, and their storage is a crucial problem nowadays. 500 cubic meters. Where do you intend to place them? Do you see the way to go on with that? There is no way further. The system was like that. Take the Soviet Union, for example. They thought all waste could be discharged to nature. They thought of discharge into lakes, rivers, and so on. But you can't do that. In 2011, Russia, being the largest nuclear power, adopted the federal law on radioactive waste management for the first time. According to the law, import of any radioactive waste into the territory of our country was prohibited. And since 2011, there are producers' liabilities include financial responsibility for disposal of all types of waste generated in the process of using the atomic power. The state keeps control of the whole process of radioactive waste handling, starting with site location for disposal, issuance of licenses and permits. It is very important that this site meet the latest safety requirements, including environmental safety. That is why the company of Rosatom and our nuclear industry make research on how to dispose the waste safely for the centuries to come. The new law encourages enterprises to reduce massively critical process industry, leading to the less volume of waste. But let's understand what is being meant under the radioactive waste. According to the IAEA, all radioactive wastes are divided into high-level, medium-level, low-level, and very low-level active wastes. Together with allocation by activity, there is class ranking in Russia. The major part of the radioactive waste is constituted of middle-level, low-level and very low-level wastes. This is of no value and no subject to further use. For example, medical equipment, tools or special work clothes. Spent nuclear fuel, which is extracted from nuclear reactors, is considered a valuable resource that can be used in the future for production of the new fuels. And it contains almost the entire periodic table. Therefore, such fuel has nothing to do with radioactive wastes. But there are radioactive wastes being the result of its processing, same as from all their stage of the nuclear fuel cycle, as well as from scientific, medical and military-industrial complex activities. The key challenge of today is how and where to store the waste accumulated for decades and still being in temporary storage. In 2014, the specialist of the National Operator for Radioactive Waste Management announced completion of project development from the Underground Research Laboratory. By the mid-20s, after finalization of all approval and public discussion stages, scientists will conduct a huge research work in the massive rock at a depth of 500 meters near Zheleznogorsk to find out finally whether it is safe to store long-life, high and middle-level radioactive waste here. Anyway, first things first. Zheleznogorsk is a town with more than a half a century of atomic history. But few people know that until 1994 this town did not exist. There was a closed administrative territorial entity called Krasnoyarsk 26. We get to Zheleznogorsk with a special pass through a guarded checkpoint. The town still has the status of the restricted one, all because there is strategic object in its territory, namely the Zheleznogorsk mining and chemical plant, being the place of production of weapon-grade plutonium for half a century. In 2010, the last nuclear reactor was stopped at the plant, and the problems of storage and processing of accumulated and produced radioactive wastes were actively addressed here. Before you get to the site allocated for construction of underground laboratory, we change from an ordinary minibus to a powerful cross-country Ural. Other vehicles are impossible to drive here. Here is the end of the road, given the turn to the wild, impassable taiga. The underground laboratory will be constructed at this place, not far from Zheleznogorsk, in order to study the possibility of storing radioactive waste here. After the safety of storage is evidenced, it will be transformed into the final disposal repository. The underground research laboratory will be located in Nicik Rock at a depth of about 500 meters. It will be a two-level complex connected by vertical wells. Scientists will place special cases with simulators of heat-degenerating high-level wastes, there to understand the behavior of the dangerous substances in the Earth's stratum. The first core target is to study the insulating properties of the rock mass in the laboratory. As a matter of fact, it is very difficult to study the rock in detail without establishment of such laboratory. The second very important task of this laboratory, which I would like to stress out, is to work out the main elements of technology to create our production runs and to practice the main elements of transport and technological operation full-scale under the ground without containers and with the transport and transfer equipment that will perhaps later be used at this facility. The site near Zheleznogorsk was carefully selected. It was chosen from 20 advantageous sites. The most important selection criterion was hydrogeological characteristics of the rock. I'm in the town of Kansk, on the territory of Ivanovo exploration expedition. Its specialists were engaged in research and drilling of rocks for the future underground research laboratory. And here is one of the mobile drilling rigs. More than 100 samples of rock were tested during the work. And here's how it happened. The rig makes a well in the rock. The raised samples are cut into equal parts, and a special hydraulic press is used to check the breaking down point. I'm holding a sample of gneissic. It is unique of its kind. Its age is about 3 billion years. It was extracted from a depth of 500 meters, and it is 1.5 times stronger than granite. It is an ideal natural barrier for protection against radiation. Now we will carry out destructive testing. Out of the 4 samples, this turned to be the most durable, withstanding a pressure of 1,367 atmosphere. Radioactive waste deep disposal technologies are under country's investigation by the leading countries of the world. Underground research laboratories have already been established in Belgium, Finland, Switzerland, Japan, Sweden, USA and France. We are looking for the underground location, as the geological barrier is deemed the most reliable one. This is a so-called deep-layered system of multi-barrier protection, which consists of engineering barriers and the geological barrier, namely the environment. The fundamental difference is only way radioactive wastes are stored in different countries. For example, Finland and Japan store their waste in granite. The USA and Germany in ancient salt layers, France in clay. Russian nuclear scientists have counted on gneissic rock. Developers and designers of the underground laboratory calculate all possible risks. Thus, a serious threat for the future object can be natural factors, such as rainfall or floodwater, which is a result of the Yenisei proximity. However, the location of the underground laboratory is chosen in such a way that any flood situation, the object will remain safe. Rim of Yenisei. It is in Yenisei region site of 120 meters. Even in case the wave of the detention reservoir will come up, not splitting over the territory, it will be just 220 meters. Zhelezny Gorsk is sure to drown. Our storage is at height of 350 to 400 meters. This wave will never come up to us. According to scientists, the future underground laboratory will stand the possible earthquake. Although studies show that measuring by 12-point intensity scale in Nizhnekansk massif the maximum earthquake magnitude in 10,000 years is less than 6, and technological objects are designed to withstand magnitude 8 earthquakes. And like granites, gneisses have higher elasticity, so they are more preferable. For example, in the event of an earthquake, granite will certainly crack, and for gneiss it is unlikely to happen. Moreover, the strength of the gneissic rock provided the scientists with opportunity to assume that radionuclides will move more slowly than on the Earth's surface. The future underground laboratory will have a complicated system of engineering barriers. It's constructed like a nested Russian doll. To start with, the compressed medium and high-level wastes will be placed in steel barrels. Then they will be packed in container, 3 barrels in which one, and filled with bentonite. 18 insulating containers will be lowered into the production well. There will be a thexotropic bentonite-based mixture between the containers to ensure the absence of cavities. Bentonite is a special montmorillonite clay. It is a natural material. Why this one? This material has a very high absorption capacity. And when there is water in it, it is capable, let's say, to swell and waterproof the object we are protecting. An underground laboratory should be built by 2024. And from that moment, a new stage of research will start, until experts are finally convinced that placing radioactive waste near Zhelezny Gorsk is safe. Even today, we can declare that creation of the underground laboratory is a timely step to ensure environmental safety. Moreover, this is required by the international rules of waste management, and world practice evidences that such projects are in successful operation around the world. I am in France, which is the country with the largest nuclear energy industry throughout Europe. More than 50 nuclear power plants provide energy not only to residents of the Fifth Republic, but also to the nearest Germany, Great Britain and Italy. Developed nuclear industry is accompanied by a large amount of radioactive waste. Therefore, research is being conducted in France for more than 20 years to understand whether it's possible to bury waste in deep geological formations. The place of birth of the Department of Meuse is in the northeast of France. Since 2005, there is an underground research laboratory here, similar to the one planned to be built near Krasnoyarsk. And now we will get to see firsthand the way this object operates. The underground laboratory can be reached by a special elevator. The descent takes about 7 minutes. Here, at a depth of 490 meters, studies of deep rocks are carried out to prove the safety of storage of high and medium-active long-lived radioactive waste. French nuclear scientists plan to store all radioactive waste of this category in a thick layer of waterproof clay. The main task is to understand whether the rock is able to restrain the spread of radiation and, if so, for how long. To do this, the rock is heated, poured with water, compressed and is followed, or its properties change. The advantage of argillite surrounding our laboratory on all sides is that it prevents spread of radionuclides for a very long period of time. Now, the employee of the UNDRA laboratory, Matthew St. Louis, explained that alongside the exploration of rocks, they are testing ways to strengthen the tunnels in order to understand the behavior of different types of supports over time. It's a tunnel shield with a jackhammer. We are using it when tunneling. And as we move forward, we mount a special kind of block support to strengthen the walls of the tunnel. If the experimental results-based projects gets all necessary permits, 250 to 300 kilometers of underground galleries will be built not far from the laboratory to be filled with radioactive waste for hundreds of thousands of years. France realized long ago that nuclear energy is the most environmental-friendly one. And here is the evidence. I'm holding a golf ball about 14 millimeters in diameter. Approximately the same volume of radioactive waste covers the needs of each inhabitant of France, consuming the atomic origin energy throughout his life. There is no person in continental France living further than 200 kilometers the atomic plant. However, the French are not afraid of it, as well as of proximity to the radioactive waste burial sites, because an informed resident is sure of his safety. Champagne is perhaps the most famous wine-making province in France. The finest taste of white sparkling wine is known and appreciated all over the world. But only few people know of a final disposal facility located just 20 kilometers away. Anyway, the French winemakers do not fear for the quality of their products, because the radiation background is well below the normal one here. The family of the hereditary winemaker Philippe Fourier has been growing grapes on this land for more than 100 years. His great-grandfather started with production of 5,000 bottles. Now the family owns 21 hectares of vineyards, with 250,000 bottles of champagne produced by the house of Fourier sold around the world annually. Me, my 3 kids and my wife have been working here for years. We want to increase the production up to 300 to 500,000 bottles. Our goal is to grow up to 500,000 bottles. We use organic products, avoid additives and fertilizers. We need clean limestone soil. This is a guarantee of our quality. An independent environmental expertise has been working here since 2007. They analyze the soil and the grapes several times a year to understand the impact of the burial proximity on wine quality. We are also studying the composition of mud on the river, flowing just steps from Andhra, and we have conducted a study of various vegetables, lettuce, carrots. We get normal findings. Mr. Fourier admits that since the construction of the radioactive waste burial facility, no client has left him. And this is just because the locals are aware of the activities conducted by Andhra, and communication is based on absolute trust. Every year we take about 20,000 of different samples, make more than 15,000 of tests on the territory of the radioactive waste landfill and the surrounding area, and then publish all the results. Today the most important task for us is to remain really open and transparent to public. Department of OB, there is a low-level and medium-level short-lived waste final disposal storage here, next to the vineyards. Waste of nuclear power plants operation, as well as from hospitals, research laboratories and universities are mainly brought here. Physically, these wastes are most often fabrics and tools used while working with RW, as well as various filters, and so on. Specialists subdivide this RW into radio wastes of low and medium activity, which consist mainly of short-lived radiation elements. A 3-stage scheme of technological barrier has been created at the radioactive waste landfill. The first protective barrier is packaging of radioactive waste. Sometimes waste is pressed and packed in these metal barrels. Each barrel has its own unique barcode. Having read it, the crane automatically places each barrel with radioactive waste at its predesignated location. As soon as the compartment is filled, concrete is poured between the metal barrels, and the space between the concrete containers is filled with gravel. This makes a second protective barrier. Each of these concrete compartments stores 2.5 thousand cubic meters of radioactive waste. 5 of such blocks are filled during a year. The third barrier is already nature-created. That is a waterproof clay soil, which isolates safely the radioactive waste in future. After all the compartments are filled, each of them is sealed with reinforced concrete slab, covered with soil, alternating layers of clay, sand and drainage rock. A waterproof seal is done and grassed. This huge green area on the banks of the English Channel is more like a golf course. In fact, this is how the radioactive waste landfill looks like after the completely filled and sealed for centuries. Territory control includes more than 10,000 of tests per year in different environments. For example, it is the air environment, where the indicators of air and dust are sampled, water environment, where the indicators of groundwater, surface water, and stream around the territory being sampled. Control is carried out in the field of geology, hydrogeology, coating quality, and many other indicators. The territory of the landfill is covered with a special waterproof coating. It is under a layer of soil and vegetation, which is carefully monitored and regularly mowed. However, the stuff has left several areas of the radioactive waste landfill untouched. To understand the impact of the burial proximity on the wild nature, this may seem surprising, but there are 200 species of plants on the site. There are even 6 rare species of flowers, one of which is listed in the Red Databook. Scientists are studying the possibility of preserving this species on our territory. After closure of the object, we have done a special coating and cannot allow anything to grow. We have to monitor the vegetation, especially plants with deep roots. All data on the buried radioactive waste is stored here in the local archive. It makes 11,000 of documents in total. This is an unusual paper. It is called an eternal one. The documents are kept in the archive rooms built in such a way as to minimize the risk to fire in the room. The archives can withstand a minimum of 3 hours in fire conditions. To ensure the integrity of the collections, they have several storage locations, here in the National Archives of France and the archives of other radioactive waste landfills. Nowadays, with the development of nuclear energy, scientists around the world group for answer to the main question: how to keep information about radioactive graves for centuries and pass it on to the future generations. In addition to paper works, we also perform experiments to record information on sapphire discs, as the stone is less susceptible to decomposition than the paper in the course of time. But the main question is whether anyone will be able to understand modern French, Russian or English languages in 50 to 1,000 years. In this situation, the solution is to have the system of symbols common to everybody. Few people know that more than 1,000 temporary storages of radioactive waste are in successful operation on the territory of our country. One of them is located near the capital in Sergiev Posad, the Orthodox center of Russia, which is visited by hundreds of thousands of tourists every year. Let us take the Radon enterprise. It has specialized in management of medium and low activity radioactive waste for more than 10 years. Here, in addition, temporary storage, the whole package of works with waste is carried out, namely their collection, transportation, processing and condition. The ultimate goal is the long-term isolation of waste collected in a fairly large area for many hundreds of years. These are Moscow, the Moscow region, and 10 provinces surrounding the Moscow region. And the area of company operation is expanding in recent years to the supply of waste from nuclear power plants, for example, Kursk, Novovoronezh, and others. Specialized vehicles are used to transport radioactive waste. They were designed by the staff of Radon. There are automated sensors installed in the cabins of the special vehicles that respond to the slightest excess of the permissible background radiation, and in case of danger, they provide audible and visual alarms. Don't be scared, but radiation devices are all around us. They are in hospitals, factories, construction sites, airports, metro, and even in technical universities. Isotopic equipment is able to detect diseases and treat them. You need radiation even to measure the level of it. With the help of a special X-ray system, you can see the type of waste in the package. Have a look yourself. Here is a fragment of quartz lamp used to disinfect the hospital rooms, and this is an ordinary nail. The irradiated plants and their stuffing need to be safely isolated in the course of time. That's what radioactive waste landfills are needed for. This device is called an X-ray television infrascope. Such ones are installed at airports and railway stations. There is only one difference. This band is used to trans-illuminate the luggage with radioactive waste. All waste should be in a stable physical and chemical form. That is, they should not contain any organic, combustible, loose or liquid components. We see an image of what is inside packages on the monitor screen. So, we can zoom in here, zoom out. Look at it from different angles. We see water in a bottle here. If a waste substance is detected in the package, it is placed in a special sorting box, where the water will be extracted. After that, the package will be sent for further processing. All the radioactive debris that is parts of medical equipment, gowns, gloves and glassware, and placed in such 100-liter barrels. Then they are sent to this supercompactor. Under the pressure of 1,500 tons, the barrels are transformed into compressed briquettes. 5 or 6 of these briquettes are placed further into 200-liter containers and then sent for a long-term storage. After pressing and packaging in containers, radioactive wastes are conditioned. They are filled with a special cement-based matrix material. Condition is a preparation of packaging suitable for a long-term insulation. It is preparation of packaging which will be in the construction for its placement for hundreds of years. Low and medium active waste is stored in a surface vault. The facility consists of 20 standard stand-alone modules, each of which can store more than 1,500 of containers with radioactive waste. All packages sent for storage are subject to strict accounting. You can find out at any time the date, the enterprise and the amount of the delivered waste. Radioactive waste will be stored here until a final disposal facility is built. The Atomic Energy Information Center has been operating in Krasnoyarsk for several years. Everyone, starting from school children and students to parents and teachers, can find answers here to any questions related to the nuclear industry. We have asked the children just one simple question: what do they know about radiation? It is a natural irradiation that comes mainly from the sun and the earth. It is present in the air. Radio engineering, even at the form of radio waves. Radiation is a natural phenomenon which every person has. It depends on weight and consumed products mostly. And the fact is that radiation is not dangerous in small doses. Today, many of us are cautious and distrustful of the topics related to the establishment of radioactive waste final disposal storages. However, these fears are only due to the fact that we have little awareness of this issue. But there was a time when the advent of railways, airplanes, automobiles and subway networks was anathema. However, these breakthroughs have made our lives and the lives of our children more comfortable and safe. Thus, you are to make the conclusions.